Welcome back to our Algebra 2 series. Today we're covering the second of a two-part series on composite functions, and this is a collection of four total examples. In this case, the composite functions that we're working with, we're not actually going to do much with the composites themselves, but we're going to find the domain of each composite function. Now, just as a quick review from the previous video, you'll recall that composite functions take us from the first bucket and they take us to the first function, and then from there, after it's finished doing whatever it has to do, then it goes into the other function and it comes out in the end. Well, the question is, what types of numbers are going to be allowed from this real bucket over here to go into the first one and then into the second? As you can see here, we're dealing with f of g of x. So the inner function is g. That'll be the first function it goes into. It'll come out as g of x, and then those numbers have to go into f. And one of the ways we take care of the domain when we're not calculating the functions themselves is we ask ourselves, what is the domain of g? So what numbers are allowed to go into g? And as you can see over here in the function itself, the only numbers that are allowed in a radical are x values that are greater than or equal to 0. Now as we move on to the next part, f of x, we see that all the answers that are coming into this g of x box are going to be the answers for our radical function g of x. And the question is, what numbers from there are allowed in f? And notice in f, this is our f function, the number the number 4 is not allowed, and so therefore we would not write x is not equal to 4, we would write g of x is not equal to 4. So that's how we kind of restrict that. Underneath here, I'm going to start constructing my domain. So the domain is going to be, first of all, immediately going into the domain is the first part, x greater than or equal to 0. And then in the second part, I have to ask myself, what about this g of x? Will g of x ever equal the number 4? Well, I don't know. I'll have to check. So let's take this number, 4, and set it equal to radical x. Will that ever equal 4? That's our question. In this case, if we were to square both sides, we would get 16. And so my question, or my statement here, is that I think that's going to be the case. I think that if there was a 16 way back here, if there was a 16 that was located in this real bucket and it went into the g function, it would come out as the number 4. And that number 4 is not allowed into f, and so that would be excluded. And we don't say x is not equal to 4 here, we say x is not equal to 16. So that would be the value that is the extra value that is excluded from our domain of the composite itself. Notice in this problem we don't actually calculate the composite. We're simply calculating the domain of the composite. Let's try this one. For the following functions, find the domain for f of x and g of f of x. So let's start with the first one for part A. F of x is f of x. So I don't want to calculate the actual f of x. I just want to look at the domain possibilities here. So there's no reason to actually do the algebra. We just want to calculate what are the numbers that are allowed. Let's go back to the same analysis we did in the last problem. In this case, though, we're putting numbers into the f function. They're coming out as f of x values, and then they're going back into the f function again and coming out as f of x values. This is our real bucket. So we don't even have to worry about g of x in this example. We're just going to cross that out, and we're going to look at this one over here. Notice that in the first case, the x value in the denominator cannot be equal to -1. So x cannot equal -1. Well, that means the answers over here can also not equal -1 because f of x cannot equal -1. So this is a very strange problem. But again, let's build our domain down below here. And this shows as a separate exercise than actually calculating the composite itself. First of all, we carry this number down. X cannot equal -1. And the second thing we have to do is ask ourselves, well, will f of x ever equal -1? This part here. So I'll take f of x, which is 2x minus 3, over x plus 1. And I ask, is that ever equal to -1? That's my question. I'm running out of space here, so I'm going to do this down here. I'll multiply through by that x plus 1, giving me 2x minus 3 is equal to negative 1 times x plus 1. And I think we'll solve this out. 2x minus 3 equals negative x minus 1, or 3x equals positive 2. So it looks like we found our culprit. X is equal to 2/3. That's the number that must have produced the negative 1 in the second bucket there. So I'm going to write as my domain restriction, x cannot equal positive 2/3. And that would be the second one. So the first domain restriction always comes from the first function that we're plugging in. And then the second one has to come down here. But notice that it's not the value here. Instead, we solve it out to find the true culprit, which turned out to be 2/3. And finally, let's do the last one, which is, oh, let me check what that was, a g of f of x. So we have g of f of x. So we've got our two values here. We've got our f of x, and we've got our g of x. And we want to calculate g of f of x, or the g of f of x. And we're not going to do the actual calculation. We're simply going to look at the domain of this composite without actually doing any other work. In this case, of course, the f is the inner function, or the first function, and then g is the second one. So here we are with the same computations we've been doing before. I'm going to cover this all in blue here, x such that. In the first case, f will not accept the number negative 1. Put that right in there, not equal to negative 1. Oh, that's not a very good negative 1. Let me rewrite that. Negative 1, that's better. And then in the g function, we see right here in the denominator the number 2 will not work. And so what we'll write here is that f of x, because here's our f of x bucket here, f of x is not equal to 2. And of course, on the side then, I'm going to ask myself, is f of x ever going to equal the number 2? I don't know. Let's check. 2x minus 3 over x plus 1 equals 2. Let's find out. Multiplying again the x plus 1 on both sides, I'm going to slide this up a bit here, we get 2x minus 3 is equal to twice x plus 1, or in this case, 2x minus 3 is equal to 2x plus 2. And I'm getting a bit confused here because as I move the 2x to the left side, I get 0 equals positive 5. Now what this tells me that 0 is never equal to 5. So we will never get the number 2 from f of x. We just will never get that, because right here you see that f of x, the question was, will it ever equal 2? And the answer is no, it will never equal 2. Our variables drop out and we get an inequality here, 0 equals 5. Well, what that tells us then is that this will be our final restriction. Only one restriction here, and that's because the value will never be attained. Now, this is a very strange concept, and I'd like to summarize and finish this out by showing you what's going on here. You see, in the problem itself, we're saying that if the real values must produce the error in the second function. And that, of course, is the number 2. We know that 2 is the value that has to be. But the problem with f of x right here is we learn in one of our earlier sections that there is a horizontal asymptote that is 2 over 1. So what happens is it will never really hit that value, the number 2, and it happens to coincide. It just is a coincidence in this case that it coincides with the denominator of the other term. So that's why it occurred down here, graphically speaking, but it also shows it algebraically, why that happened, that we got no value 2 for f of x. So it kind of checks itself. So that's kind of a summary of it. But this is a great little exercise to calculate, and let me go back to the top here, to calculate the domain of a composite for a composite set here. All right, there you have it.